Hello learners, this class is for second year, fourth sem. The chapter name is interference and today's topic is Lloyd's mirror experiment. Okay, so this is the diagram that you are seeing here for the experiment of Lloyd's mirror. So this is a Lloyd's mirror. You can see in the diagram this is a Lloyd's mirror that is polished in the front side and that is blackened at the back side because we have to avoid the multiple reflections. So to avoid these multiple reflections we are blackening at the back end, okay, polishing at the front end to get the nice reflections. Okay, this is termed as MN. Okay, this is a screen on which we can see the pattern. The screen is named as PQ. Okay, next there is a distance D from the source to the screen. From the source to the screen, capital D is the distance. To virtual sources distance is small d. Okay, so we are inserting a light on the grazing angle, at the grazing angle. That means here, not at the horizontal line of the mirror. Here we are inserting the light, and here. So we can say it is at a grazing angle. Okay, grazing angle. Then it is reflected back like this here. Okay, this here. Okay, this is that is virtual. uh, from the PQ screen one can see as if the light is coming from here. So this one is a S1 virtual source and this will be the virtual S2 source. Okay, so this is about the diagram. Now let's see the theory part. So Lloyd's mirror is polished on front and blackened at the back to avoid multiple reflections. Lloyd mirror is a plane mirror MN. PQ is a screen. A narrow slit S1 is illuminated by a monochromatic source of light. So we are illuminating a monochromatic source of light. Further, light from slit S1 is allowed to incident on the mirror MN at grazing angle only. Okay, so the reflected beam appears as if it is coming from S2. So that is a virtual source. And S1, S2 here serves as coherent sources. The direct cone light P(S1Q) and reflected cone of light P(S2B) superimposed over each other and they produces the interference fringes. Now we will say P(S1Q). See, where is the P(S1Q)? P(S1) and Q. Where is our Q? This is the Q. Okay, this is like this. P(S1Q). And another one is P(S2B). P P(S2B). Okay, these are the two, what we say here, reflected cones that are superimposing over each other, and because they are superimposing they produce the interference fringes as they overlap on the region PB. Where we observe, we can't find central fringe. So when we are observing from the eyepiece, we cannot find the central fringe. So what we have to do, we have to adjust and bring the screen to the we adjust and bring the screen to some position that we can see the central fringe. Because we are not able to see the central fringe now, we have to adjust the screen and see the central fringe. Okay, so when we are adjusting the central fringe, when we are adjusting to see the central fringe, we are bringing the screen forward. Okay, we are bringing the screen till it touches the end of the mirror. Okay, now when the screen touches the mirror, that time we can see the central fringe. Now we can see the central fringe when we are bringing the screen or adjusting the screen towards the end of the mirror. Okay, unlike the Fresnel's biprism, now it is not bright fringe at the center, it will be dark. Okay, dark fringe. So why we are getting the dark fringe? Because as we have seen in the Stokes law that on the reflection there will be phase change of 180 degrees, no, that is why. So this is because the reflected beam undergoes a sudden phase change of pi or 180 degrees on reflection. Due to reflection it undergoes a phase change. So due to phase change the bright fringe has changed to dark one. So what is the path difference? S2p minus S1p is equal to n lambda, where we get a minimas, the destructive interference, and S2p minus S1p is equal to 2n plus 1 lambda by 2 when they get maxima, that is on constructive interference. So these conditions for maximas and minimas are opposite to that of the conditions for Fresnel's biprism. So totally oppositely different. Okay, for the maxima's condition will be for minima, and minima's condition will be for maxima in the Lloyd's and Fresnel's respectively. So now this is the way that Lloyd's principle work, Lloyd's experiment work. Now we have to find out the wavelength. So to find out the wavelength, fringe width we know beta, that is to be measured by the micrometer of the eyepiece, and d, small d is we can use the lens displacement method, and we can find out small d by using the convex lens and displacement method. Next we can find out d directly by using the scale, and we have to substitute at these places, then we'll get the lambda. This is the experiment of Lloyd's mirror.